You are about to learn how to make your own AI, quantize it, and then run it on your custom hardware. To make this process as entertaining as possible, all details and resources are on the GitHub for you to explore it at your very own rhythm. So let's start, and hope you enjoy this video. First of all, I suggest you use a Linux-based OS. Windows may work with Docker, but anyway, I suggest you use a VM, at least for the notebooks. In order not to be bothered by any annoying errors while working, we need to set up a working Docker environment. To do so, I start by sourcing my environment variables, and I use the fin bash script, and all of the details are in the GitHub to use it properly. Now that we have everything set up, we can start working on our AI model in the tutorials notebooks. To do so, we'll use Brevitas. Brevitas is a tool that allows us to train and quantize neural networks. Before going any further, if you struggle with some concepts, you have all of the learning resources in the GitHub. Brevitas works just like PyTorch, so you should be good to go if you know your way around AI in Python. In the GitHub, we use a simple, fully connected classifier to recognize and classify clothes from the fashion MNIST dataset. Here we declare a network just like we would in PyTorch normally, but the thing is that we use quantilinear or quant_relu as activations. We use a weight bit width quantization of the weight, and the same goes for the activation. Here, bit width equals to activation bit width. We now train our neural network. Brevitas will handle the quantization aware training in the backend. Now we can train our neural network. So it's actually extremely simple, as it works exactly like a regular PyTorch. Just note that quantize aware training will take a little bit more time than regular training. Now that we have our quantized neural network, we can simply export it to Onyx in a thin Onyx format, which allows us to represent the quantized neural network correctly. We can now use Neutron to visualize our neural network as a graph representing the tensor operation that happens within our AI. Now that we have our quantized AI model, we have to convert it to hardware. This task will normally be a huge pain, but thanks to Fin, we will be able to simply use an API to manipulate our model's graph. The idea here will be to use a model wrapper and pass it through a set of network transformation. Each transformation has a specific role that are detailed in the notebooks. So following the notebook, you'll be able to learn about all of the important transformations, especially the ones at the end that generate HLS code from the layers, which in turns gets converted to hardware by Vitis HLS. What is an HLS conversion? What we want to do is generate HLS code from these MVAUs. So HLS is just a way to describe logic using C and C++. So this will be handled automatically by Fin. Now that we have an HLS representation of our model, we can run design synthesis, which will convert all of the HLS codes and RTL snippets into an actual IP we'll be able to use. You can see I ran the actual hardware build. As you can see, it created 3 data flow partitions, an input DMA, an output DMA, and our actual model represented as hardware. Now we are pretty much done. If you have a compatible board, you can simply use a Fin API to run inference using the PYNQ API. Unfortunately, I do not have the supported boards, meaning I will grab this opportunity to show you how to do it manually like true hackers. Okay, so now we have our AI as an hardware IP block. All that remains to do is to actually use it. When it comes to running inference, it really depends on your application. But for this example, I made a very simple scenario where we load 100 images in memory and feed it to the model to just check if it works. Before launching the Xilinx tools, we first need to locate where the Vivado project is actually located. CD into Vivado Zinc project. There we go, and I will open Vivado on this fin.xpr file. So there we are. I will directly open the block design. Okay, there we go. Then get rid of absolutely everything, except the AI model represented by the streaming dataflow node. Now we use the block design to put our Zinc processing system in place. It simply is an ARM CPU, by the way, and it will allow us to control the FPGA by running some firmware on it. And we also take some time to add and configure DMA and run the block's automations. I then add a custom FIFO to interface between the model and the DMA. Otherwise it just doesn't work because there is no TLAST signal, which DMA doesn't like. To do so, I open a new blank project and add a single source file containing the HDL code from the GitHub. And then I simply package the IP into an IP repo and added this repo to my main project and use the custom FIFO IP in the design between the model and the DMA block. I also forgot before to connect the DMA to DDR, so I fixed this problem by adding a high-performance AXI port in my Zinc processing system. This allows me to simply run two connection automation, thus connecting the DMA to DDR. I also grabbed the opportunity to add some debug probes, which allows me to run another connection automation and add an ALA debugger. This will allow the use of probes on live signals, which will allow us to do some debugging later on. And voila. Okay, we are now done. To run inference, I export the hardware to Vitis and copy-paste the firmware from the GitHub in a new application. I have a tutorial on how to write your own firmware on my channel for DMA, and you can find the link in the GitHub resources. Then we need some samples. To do so, you have in the GitHub a Python script that generates data. Write it in a header file that you can simply copy and paste in your application source code. Now everything is ready. We can simply test it by plugging in our Zinc board and running the application in Vitis. I will go back to Vitis, launch. Okay, apparently it worked. Okay, so we do have some problem here. Okay, we have a problem. Now it's time for the debug. After analyzing the signals, I figured the model did classify the sample right indeed. It's looking pretty good, actually pretty decent. But the data had some trouble making it through DMA, thus the UART giving me some very wrong values. My first instinct was to blame myself, and the way I tried to make DMA work with 8 bits. To solve this problem, I switched all of my configs back to 8 bits, except for the DMA that I switched back to 32 bits. To fix the data width gap between the DMA and the custom FIFO, I made the interface connection manually. And now I rerun everything, and for the moment of truth, and there we go. Accuracy 90%, it worked. What about this, our debug probes? As you can see here, it is indeed a lot better. Okay, so welcome your faces back in Facecam once again. Yes, I did have an haircut indeed. So first of all, I want to thank you all for all of the attention you gave to my previous video, which really goes a long way for me. So my main goal with this channel was to build a great portfolio for me and make myself as employable as possible, you know. And it just makes me so happy to see that you can get some value out of it, like you can actually get something out of it, that some of you actually enjoy the content. That being said, I'm cooking some more vids in the back end, and I think I will focus more on the non-technical stuff and more of the reports that I can do of the different projects that I do. I think it is way more enjoyable for you and for me to do and watch. And yeah, I will still do some actual technical nerdy content, but more on actual tutorials on GitHub that you can do at your own pace. I think it is way more valuable for you. So yeah, like this, all of the curious can go and do the things at their own pace, and you can enjoy the actual content that I do and that I enjoy doing for you.